All right, let's dive in. Today, we're going to wrestle with a classic vector dynamics problem. Now, I know at first glance it might look like a real beast, but I promise you, by the time we're done here, you'll see how a simple, clear strategy can make even the most intimidating problems totally solvable. You know the feeling, right? You're staring at the page and it's just a word soup of vectors and Greek letters. It's so easy to feel lost before you even start, but here's the secret. Physics isn't just about memorizing formulas. It's about having a game plan. It's about learning how to turn that jumble into a step-by-step path to the answer.
Okay, so here it is in all its glory. Let's just read it together. We've got this thing, angular momentum m, and it's changing over time based on this formula. We're also told we have two vectors a and b that are constant. And here's a huge clue. They're perpendicular to each other. Our mission, should we choose to accept it, is to find the force moment n at the one specific moment in time when the angle between n and m is exactly 45 degrees. I know it sounds like a lot, but don't sweat it. We're going to break it down.
Okay, first things first. Before we jump into any crazy math, the most important step is to just stop and take inventory. Let's figure out what clues the problem has actually given us. Let's list out our knowns.
First up is this m vector, the angular momentum. So what is this thing really? Well, the easiest way to think about it is that it's just like regular straight line momentum, but for things that are spinning. If something's got a ton of angular momentum, it's going to be really, really hard to stop it from spinning. And then we've got the force moment, vector n. You probably know it by its more famous name, torque. It's a perfect parallel. If a force makes something speed up or slow down in a line, torque is the twist that makes something speed up or slow down its rotation.
So, let's put it all on the table. We have the exact formula for m, we know vectors a and b don't change, we have this critical piece of information that they are perpendicular to each other, and our whole goal is to find n, but not just any n, the n at the exact moment the angle between it and m hits 45 degrees.
So we have our pieces laid out. We've got m, we need to find n. How on earth do these two things connect? It's like we're missing a bridge between them. Well, it turns out there's one single beautiful equation in physics that is that bridge. It's the key that unlocks this entire problem. And here it is, boom, n equals dm/dt. This is the absolute heart of the matter. All this equation is saying is that the torque is simply the rate of change of the angular momentum. If you know how m is changing with time, you automatically know what n is. It's that simple. And you know, this should feel kind of familiar, right? It's the spitting image of Newton's second law. We all know that force equals the rate of change of linear momentum. Well, torque is the rate of change of angular momentum. It's one of those beautiful, elegant parallels that nature gives us for free. Okay, enough talk. Theory is great, but let's get our hands dirty. We have our weapon of choice, n equals dm/dt. Now let's actually use it. Time for our first big calculation. We start with our core equation and we just pop in the expression for m that the problem gave us. Now we just have to take the derivative with respect to time. And remember, the problem told us that a and b are constant vectors. They don't change. So what's the rate of change of a constant? It's 0. That first term, ddt of a, just disappears. For the second term, we just use the good old power rule. The 2 comes down and we're left with 2bt. And just like that, we have our formula for n. Fantastic. We now have expressions for both m and for n. We are getting so much closer. Now we need to bring in that other major piece of the puzzle, that 45-degree condition.
So let's take a quick time out. Let's think like a physicist. When a problem hands you an angle between two vectors on a silver platter, what's the first tool that should immediately pop into your head?
Yep, the dot product. It's like a magic translator. Its superpower is that it takes something geometric, like an angle, and turns it into pure algebra, something we can actually solve. It's the perfect tool for this job, no question. So let's put it to work. We just swap out the generic a and b for our vectors, n and m, and we stick in 45 degrees for our angle, theta. And there you have it. This equation right here is our new roadmap. All we have to do is calculate each piece of it. Now, this might still look a little scary, but we're just going to tackle it one piece at a time. First, we'll figure out the left side, that n.m. Then we'll get the magnitudes for the right side. And the cosine of 45, well, that's just a number. We got this. Let's start with the dot product. Okay, so we substitute in our expressions for n and m, and then we distribute the terms. And watch this. This is the magic moment. Remember that clue from the very beginning, that a and b are perpendicular?
Well, the dot product of any two perpendicular vectors is always 0. So this first term, 2t times b dot a, it just vanishes. Poof, gone. Which makes our lives so much easier, leaving us with just 2b squared t cubed. Next up, the magnitudes. The magnitude of n is pretty simple. It's just 2b. For m, we have to be a little more clever. Since the vector a is perpendicular to the vector b, it's also perpendicular to bt squared. That means we can think of a and bt squared as the two legs of a right triangle. And how do you find the length of the hypotenuse? Good old Pythagorean theorem. It's just the square root of the sum of the squares. Okay, assembly time. We've got all our parts. We take the dot product and put it on the left side. We take our two magnitudes and the cosine of 45 and put them on the right side. And just look at what happened. All that complicated vector physics has boiled down to one single algebraic equation, where the only thing we don't know is the time t. We are on the home stretch. We've successfully translated the physics into the language of algebra. The physics part is basically done. Now it's just us versus this equation. Let's solve it and bring this thing home. So let's start cleaning this up. We can divide both sides by 2bt to simplify it a bit. Now we've got this nasty square root. What's the best way to kill a square root? You square both sides of the equation. When we do that, the square root on the right just disappears. Now we just need to gather up all the t terms. We can multiply both sides by 2, then subtract a b squared t to the fourth from both sides. And look at that. We're left with a beautiful, simple result. T is the square root of a over b. But wait, we're not quite done. Read the question again. It asked for the force moment n, not the time t. This t is just the instant when the angle is 45 degrees. So for the grand finale, we take this value of t that we just found and we plug it right back into our formula for n. And there it is. That's our answer. That is the force moment at that specific instant. So what's the big picture here? What should you really take away from this? First, never forget that fundamental link. N is the derivative of m. Second, don't be scared of vector calculus. And third, if a problem ever mentions an angle between two vectors, you should be screaming dot product in your head. But the most important thing is the strategy. Unpack what you know, find the core principle that connects everything, and then just execute the math piece by piece. And I'll leave you with one last thing to think about. We saw this amazing parallel, right? How the laws of rotation mirror the laws of motion in a straight line. This isn't a coincidence. It's a deep pattern in the universe. So my question to you is, what other fundamental laws that you know for linear motion might have a secret rotational twin just waiting to be discovered? Thanks for joining me on this one.